All right, so we're taking a look at 5.4 today, learning how to take a derivative and integral of e to the x, just mechanically working through that derivative and integration process of a brand new formula. We're going to review all of these formulas because, well, we need to memorize them. When you go to take your AP test in May, there is no formulas given for anything related to calculus. So, what is the derivative of u to the n? Power! And bring the power down and reduce the exponent by 1. So we have n times u to the n minus 1, but my independent variable is not the same as my derivative variable. So times u prime. If you forget that u prime on a memorization test, I'm going to have to mark those wrong. All of these are set up as chain rule. The derivative with respect to x of natural log of u is u prime over u. Let's not forget the domain of natural log is x is, or in this case u, would be greater than 0. We don't need the absolute values around the u because if an expression, if you're given a logarithm, obviously with an expression inside, it's already implied that domain is greater than 0. We're going to have to remember to include the absolute value, though, when we do the integration. What's the derivative of sine of u? Cosine of u, u prime. Derivative of cosine, negative sine of u, u prime. Derivative of tangent, secant squared. So the derivative of tangent of u is secant squared u, u prime. Derivative of secant of u. Ooh, you're making me excited. Secant u, tangent of u, u prime. Cosecant. Negative cosecant of u, cotangent of u, u prime. And the derivative of cotangent, negative cosecant. Yep, negative cosecant of u squared times u prime. Don't forget, it doesn't sound like anybody's forgetting anything. Those are nice choral answers. All of your cofunctions, your cosine, cosecant, cotangent, the derivative of all of those cofunctions are going to be negative. You'll happen to see that same pattern when we do derivatives of inverse trig functions coming up soon. Well, if you know these derivative rules, you know the inverse operation, the integration. What is the integral of u to the n? A variable base, fixed power. Power! So we're going to raise the power up. I always do that first to remind myself of what I'm going to divide by. So u to the n plus 1 over n plus 1. And don't get lost in a sea of desperation. All your indefinite integrals will yield a function. When you take the derivative of a function, if there's a vertical shift, if there's a plus c, the derivative of a constant is 0. So when you go to integrate, without additional information, you're not going to be able to find what that c is. So these are general solutions to these integrals. The integral of 1 over u du, which I will very often, nearly always say instead, or label as the integral of u prime over u, natural log of the absolute value of u plus c. I always verbally mentally say this in my mind, the derivative of sine is cosine, the derivative of cosine is negative sine, to remind myself. I do the derivative rules first to remind myself if there's a sign change. So if the derivative of sine is cosine, no sign change, the integral of cosine of u du is sine of u plus c. If the derivative of cosine is negative sine of u, u prime, then the integral of sine of u du, negative cosine of u plus c. The integral of secant of u squared du, tangent of u plus c. Integral of cosecant of u du, negative cotangent of u plus c. Integral of secant of u, tangent of u, secant of u plus c. And then our last one, the integral of cosecant of u, cotangent of u du, negative cosecant of u plus c. Okay, our last column here is, I've was writing this out, and I put the red ones as the new ones, the derivative and integral of e to the x, but as I already admitted, I forgot to give you in 5.2 the integral of tangent of u du. This integration rule is very easy to derive if you just see the tangent of u as sine of u over cosine of u, and then go back to your integral of u prime over u. But we're just writing the answer basically. So what is the integral of tangent of u? Negative natural log of the absolute value of cosine of u plus c. If you see that tangent, I'm going to go ahead and say this anyway. If you see that tangent as sine over cosine, u is in the denominator. The cosine of u is your u. That's why the integral of u prime over u is the natural log of u. The denominator of tangent is cosine, and that's why we have the natural log of the cosine of u. But then if the denominator is cosine, u prime is negative sine of u. That's why we have a negative from the inverse, the integral of tangent of u du. That's where the negative's coming from, and the negative natural log of the absolute value of cosine of u plus c. The integral of cotangent of u, where we have sine in the denominator, is just a positive natural log of the absolute value of the sine of u plus c. Now, we don't honestly integrate secant and cosecant that often, but they can show up. In terms of these rules, the answers to the integral of secant of u, I'm asking for the integral of secant of u, but what's the derivative of secant of u? Secant tangent. So we have the natural log of the absolute value of the secant of u plus, now of course it's not the derivative rule, and it's not an exact inverse relationship, but the integral of secant of u does involve secant of u tangent of u, just like the derivative of secant involves secant tangent. So that's a kind, in terms of like, if you forget that rule, maybe that'll help a little bit. So the integral of secant of u du is equal to the natural log, and I want to make sure that this is right. Get my plus minus right. Yeah, so we have a positive natural log of the absolute value of secant of u plus tangent of u plus c. And then the integral of cosecant of u, the derivative of cosecant of u is negative, so negative natural log, and it's, where's it at up here? Negative cosecant of u, cotangent of u, u prime. So we have a nice tie-in with the negative coefficient. Of course, in the natural log, the cotangents in cosecant and cotangent are not being multiplied, they're being added. But one last time, the integral of cosecant of u du is negative natural log of cosecant of u. Come on, hand, agree with my mouth. Negative natural log cosecant of u plus cotangent of u plus c. Now we get the world's easiest derivative and integration rules to memorize. The derivative of e to the u. Come on, e to the u, and everybody else, a lot of other people said it too, times u prime. And then the integral of e to the u du is e to the u. It's like the answer is the question. It's so awesome. Okay, so let's start going through some examples. We do want to, I'm not going to spend a lot of time on this because we already have in the past, but we do want to remember, stick with me, we do want to remember that y is equal to natural log of x. That is, y is equal to log base e of x. Not that you will ever write this because, natural log, the base of e shows up a lot in nature with compound growth and decay of like compound growth of bacteria or cells and compound decay of say carbon for like maybe say carbon 14 dating. But y equals natural log of x is a function that has a vertical asymptote of x equals 0, it passes through the coordinate before transformation of 1, 0, and has a domain of x is greater than 0 or all real numbers greater than 0 and a range of all real numbers. The inverse of y is equal to the natural log of x, logarithms and exponential functions are inverse math operations, to hopefully remind you of that. So y is equal to e to the x is exponential growth with base e. That is going to be the inverse graph. It is the inverse function of y is equal to log base e of x. So since y is equal to, now that base is bigger than 1. E is approximately 2.718. It's an irrational number very similar to pi, but more complicated to explain where it comes from. And that base is bigger than 1, thus you have a fixed base variable exponent. This is exponential growth with the base larger than 1. And all exponential growth functions will have asymptotic behavior at the x-axis, which means you have a horizontal asymptote of y is equal to 0. You have an exponential growth function that is going through the coordinate of 0, 1. And you have a domain which is the range of natural log. You have a domain which is all real numbers. And you have a range which is the domain of natural log, because the domain and range swap roles in inverse functions. So your range is y is greater than 0. And when you start talking about natural exponential growth and natural logarithms, those inverse math operations, of course, are going to come into play as you're solving logarithmic equations involving natural log, and you'll be using natural log to help you solve exponential growth equations where the base is e, because those inverse math operations will undo each other. So just keep that in mind for some of your earlier math problems where they're asking you to recall that inverse relationship. Of course, inverses graphically are a reflection over the line y is equal to x, but we're going to be spending our time for the rest of the period doing derivatives and integrals involving base e. For example number 1, we have y is equal to e to the square root of 2x plus 1. Now, whether you do this on the side is up to you. I generally would not, but with the radical and having like basically two compositions for this first example, you have a whole square root of 2x in the exponent of e, and then within the radical you have another composition of functions, which is that function of 2x. So if you want to take a little bit of time on the side, you can say u is going to be 2x to the 1/2 power. So then du is going to bring the power down. So 1/2 times, we've got the 2x, the base inside the power of 1/2. So we're going to subtract 1/2 by 1 and get negative 1/2. And then finish in the chain rule, because we have a composition within a composition. We have we have our u of 2x yielding a u prime of 2. And of course, 2 divided by 2 is equal to 1. Everybody okay with that? So if y is e to the square root of 2x plus 1, then y prime, what's the derivative of e to the u? E to the u times u prime, which is 2x to the negative 1/2 power. And since and the derivative of a constant is 0, so we have y prime is equal to e to the square root of 2x over, right? This base has a negative power, so I'm going to clean this up. Maybe it's a multiple choice question, and we're trying to match the answer. We're going to drop that square root down into the denominator and have a division of the square root of 2x. For our next example, we have y is equal to 3x squared times e to the negative x. We're going to walk through this one, and I'm going to let you try the next one on your own for a period of time. What is it going to take to find y prime for this problem? What rule are we going to have to follow? Well, product rule. So, what's that? Yeah, that's the one you're going to try on your own. So we're going to, we could make it a quotient rule because we have e to the negative x. It might even actually be better as a quotient, but we're going to leave this alone. I have found that generally, if I'm given a product, it is generally best to just use the product rule for derivative. If you're using our solution guide to help you with the learning process, I've already mentioned this a number of times, they like to take the quotient rule and make it into a product and do product rule. So I tried to do that a lot when I was relearning calc to teach it live for the first time, and I eventually came to the conclusion it's just a waste of time. It actually makes a lot of problems more complex. So product rule, that means we're taking the derivative of the first, and we're quite a few sections past this, so I'm not going to actually write all this out. What is the derivative of 3x squared? 6x. So you're taking a derivative of the first factor times the second. So 6x times e to the negative x plus, then leave your first factor alone. So we have 3x squared. And now we're taking a derivative of our second factor. And this has been on the board for just about 10 minutes now. What's the derivative of e to the u? E to the u, u prime. So the derivative of e to the negative x is e to the negative x times, our u is our exponent, our u is our negative x, u prime, negative 1. So then y prime is 6x times e to the negative x, and negative 1 times 3 is negative 3, x squared e to the negative x. Just a quick double check. And we're good. The only reason to do any additional work is if you're trying to match a multiple choice answer. So I don't have a problem with these negative exponents. So in this base of e, let me get some orange. In this base of e, we have an exponent of negative x. So as we go to take our derivative, that negative x is our u in the derivative rule. So the derivative of e to the u is e to the u, and then times u prime. And so if u is negative x, I did see the acknowledgement that you got that. Du is going to be negative 1. That's where that's coming from. Awesome. We good? Y is equal to, we've got 2 times e to the 3x over e to the 3x plus 1. And as I look at my notes, I see I did not do this, but I want to let you know and remind you that when you have a nice simple constant coefficient on your function, you may find it to be simpler to do derivatives and integrals if you move that constant coefficient out. So my notes are a little bit different, but I've got more years of experience. You may want to take this 2 and move it out in front of that function, and so you have a little bit simpler arithmetic and hopefully simplification process as you take that derivative or integral process. So that 2 in front of the e to the 3x, I would suggest maybe some of you take that 2 and move it out, in this case, in front of the derivative function. So you have a little bit simpler process simplifying your answer. All right, give it a shot. Somebody tell me what to do. Yes, quotient rules. So then we have 2 times, Lodi high, e to the 3x plus 1 times,
2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times, 2
So the low d high, so the derivative of e to the u is e to the u u prime. Awesome. Minus. So high d low. And the derivative of e to the u is e to the u prime, as you correctly said, and the derivative of 1 is 0. So we have that going on. Over low, e to the 3x plus 1 squared. Okay, now, nice job, ma'am. Now, these are multiple choice level questions. Which means you're going to be trying to match your answer with a multiple choice answer. And it will not look like this. So we need to clean this up. Now, how you do that is up to you. And I wouldn't have been doing this when I was relearning calculus, whatever it was, about 8 or 9 years ago. I would have normally just taken this 3e to the 3x and this 3e to the 3x and distributed and combine like terms. And for this problem, it really doesn't take that much effort. So if you did distribute, you would have just 3 terms in the numerator to, add together. So not a tremendous amount of work. But, since we are in calculus and we're not through with our journey yet and everything's going to continue to become more complicated, I would like to emphasize one of our favorite words in math, the F word, factoring. These two terms both have a common factor of 3e to the 3x. So instead of multiplying out and then combining like terms, which can really create a big mess, it won't be that much in this one, but all that distributive property could create a large complex equation that you don't really want to work with, you don't really want to deal with. So it's not truly necessary for this problem, but I'm going to take that 3e to the 3x and factor it out of those two terms because it will often help you out. So we've got 2 times that 3e to the 3x common factor that we have. And then what's left in our numerator is e to the 3x plus 1 minus e to the 3x, right? Because we factored out that 3 times e to the 3x from these two terms, and it's out front, all over e to the 3x plus 1 squared. And when you combine like terms, of course, excuse me, e to the 3x minus e to the 3x is 0 plus 1. So our numerator is just going to be 2 times 3, which is 6. E to the 3x over e to the 3x plus 1 squared. Let me double check, and we're good. Y prime. Bam! So going forward, when you're doing quotient rule and creating a term with multiple factors in each term, look for factoring to simplify your work. It will help you out tremendously later on in your mathematical journey. F of x is equal to the definite integral from 0 to the natural log of 2x of the tangent of e to the t dt. What's f prime? Do you remember how to take a derivative of a definite integral? It's got a nice little name. It's a nice shortcut. The lower limit is a constant. So you are set up to just pretty much write the answer nearly as quickly as you read the problem, if you remember the rule you have to follow. You learned it in 4.4. You should be excited every time you see this question on a multiple choice test because you can go through it quickly and move on to something else and have a lot of extra time to do other problems. All right. What do we need for this problem? What are we going to do? Second fundamental theorem of calculus. At least that's how our book calls it. Some books call it the first fundamental theorem of calculus. We are taking a derivative with respect to x. Nice job. I'm going to ask you for more information here in a second. But f prime of x is the derivative with respect to x of the definite integral starting from 0 to the natural log of 2x of the tangent of e to the t dt. So you know the name. How do we apply it? What's the answer going to be? Or the next step. It'll be almost the answer. It's going to involve where I'm going to write the tangent of e. We don't need to take the integral, plug in the lower and upper limits, and get a new function, and then take its derivative. These inverse math operations are going to basically cancel as long as that lower limit is a constant. So we take that upper limit and what? Plug it in. Okay? When you do, let's go on a little bit of a side journey here for a second. If I ask for the definite integral from, let's say, 1 to x of t dt, that's going to be 1/2 t squared with an upper limit of x and 1. And when you finish that definite integral process, right, don't you take these upper limits and substitute them in? So you would have 1/2 x squared minus 1/2 times 1 squared. And then our problem here involves another step of taking a derivative, but what I want to emphasize to you is that upper limit, whether we're doing the second fundamental theorem of calculus to shortcut through and not actually do an integration process, if we were to do an integration process, that upper limit does get plugged into. That upper limit does get plugged into our function. So this x will replace the t and we'll have like a 1/2 x squared. So here we have the tangent of e to the, well, the natural log of 2x is going in place of going substituted into the t. So we have the tangent of e to the natural log of 2x. Now, because we are taking a derivative of a definite integral, we're just not going through the definite integration process, we do have to finish that chain rule. And our upper limit is a function. It's not a perfect max. You know, the upper limit's not just x. It's another function. It is in terms of x, but it's a pretty complex function. So we have to finish that chain rule. So we're going to have the derivative with respect to x of a definite integral from 0 to the natural log of 2x of tangent of e to the t dt is the tangent of e to the natural log of 2x. And then we have to finish that chain rule, taking the derivative with respect to x of the natural log of 2x. And so, does that make sense? Okay. So then we have the tangent, that's natural log. We have the tangent exponential function base e being applied to a logarithmic function of base e. Logarithms and exponential functions are inverse math operations, so they're going to cancel, giving us just a 2x. So we have the tangent of 2x, and then the derivative with respect to x of the natural log of u. The derivative of natural log of u is u prime over u. So we have 2 over 2x, meaning our final answer is the tangent of 2x. Our 2's are going to cancel, so that's going to be just over x. And that's our last example involving derivatives. or taking or finding derivatives of functions involving e to the u. Little recall of second fundamental theorem of calculus. It sounded like we needed that. So